Thank you. This is going to be I would say, a first talk, maybe out of many, at least first of two. So I'm going to, make an introduction in feature engineering. The next talk will be about, maybe sort of advanced feature engineering. So, but as Sri mentioned, I do Kaggle for a living. They also forced me to build a product in H2O. Yeah, I do my best in both fields. So, yeah, the last 5 years of my life I spent on Kaggle, competing in different competitions. Usually not that good, if you can see, but not bad. So, and again, so the topic of this talk is feature engineering, and basically why I think it's very important. A lot of people across the domain, across the machine learning society, a lot of people who well known in machine learning, they agree on one thing, that feature engineering is extremely important. But basically, what exactly we can mean by feature engineering? The very simple explanation you can see on the bottom. So basically, that's the way how you can transform your input so machine learning algorithm can actually consume it and build a good predictions. That's the easiest and simplest explanation of what feature engineering mean I was able to find. And so basically, this slide is some sort of a motivation. So, considering we have a 2D space, we have a points, right, with a red and blue, and we would like to build a linear classifier which able to, classify them correctly. That's not possible actually to build this kind of linear classifier given the data, right? There's no way how you can split them, by just line actually into separate classes. But if you transform the Cartesian coordinates into polar one, they immediately become very easy to separate by just a single line. So of course you apply a quite complex transformation. You can think of this transformation as a feature engineer because you just engineer a feature for a model. But it allows you to build a simpler, maybe more lightweight model compared if you try to, let's say, fit a random forest into it. So, okay, so a typical machine learning workflow might be seen like this. So you have a data integration step. The next step will be a data quality and transformation. Then, after the transformation and data quality checking, you have a table, right? You can fit into your favorite machine learning algorithm. Each row on this table represents one single event, and each row has a target you would like to train to predict. So, and basically, that's exactly a place when feature engineering can take place, right? So, of course, you can argue and say hey, this part actually is a part of data engineering as well. But for this talk, we concentrate on this part only. This one is a way much more complex, and I would say it's a vast area for research, for future research, because there is not much research done on this area, how to combine basically available structured data to get the good data set for prediction. So not feature engineering from my point of view. So as I mentioned, initial data collection cannot be a feature engineering. The creation of target variable, because it's something you should be business driven, right? You have to have some business need to predict something for to fulfill some business goals. Removing duplicates, missing values, fixing mislabeled classes. It's more like a data cleaning. Of course, each machine learning model should be more or less, more or less stable if you put a duplicate, so a missing value on it, but it's not the goal of feature engineering. It's more like a data cleaning. Scaling and normalization is not a feature engineering by itself. It's more or less like a data preparation for specific models. Let's say, for example, for neural nets, you have to scale your data, otherwise this gradient descent won't work as you expect it to work. Well, feature selection is not per se like a feature engineering, but I'm going to mention this in this talk, in a couple of places. So basically, that's a feature engineering cycle, right? You have a data set, you have a hypothesis to test, you validate this hypothesis, you apply by applying, you create a new features based on the existing one, and you repeat this process over and over again, in pursuing of building the better model. So how you can come with what's the source of your hypothesis, basically, right? Well, obviously, if you're a domain expert, that's a significant source of your knowledge, right? That's how you actually can build different features out of your raw features. Well, if you don't have a domain knowledge, of course, you can use your prior experience, based on the nature of the data. Is it a numerical field? Is it categorical? How many category levels you have? How your numeric features is distributed, and et cetera, et cetera. That's exploratory data analysis you can help you with. And of course, my favorite part, you can use specific machine learning models, and by analyzing the model itself, you can get some insight about how the data is structured and what kind of feature engineering transformations you can use to get the better model. Okay. It's validation. Yeah. So feature engineering is kind of a hard problem, right? Especially if you're trying to apply a powerful feature transformation like target encoding, because in that type of transformation you explicitly specifically try to encode your categories using information about the target. That's something that can actually introduce a leakage to your data, to your model, and the model will be very good fitted to the training data, but it will be completely useless in a real life usage. Again, that domain knowledge is extremely important, especially if you have a specific knowledge about the nature of the data. Let's say, for example, in Chevron, if you analyze the well data, right, how well actually drilled, it's a kind of physical process, right? There is a lot of physics processes happening inside, which actually can be expressed via formulas. So that's something, the knowledge you can put inside your model as well. Well, of course, it's time consuming, especially if you have a lot of data, because you have to run your model against it. You have to test how good the feature is. And of course, to do that, you can run through 1,000 of experiments, especially if you perform like a EDA or like previous experience search. So again, as I mentioned, simple models give you better results. So ideally, it would be nice to find some golden features and just a fit linear model on top of it, right? That's would be the best possible scenario, because you prefer I always prefer simplicity over the complexity of the model. Of course, in real life scenario, it's never the case. You still have to apply like a quite complex models like a random forest or gradient boosting or neural nets to get some results. But still, like a good features can help model to approximate faster. And we can discuss like 3 key components to that. That's a target transformation, feature encoding, and feature extraction. Well, target transformation, that's something you can use to transform your target variable. That's especially useful for regression problem. Say you have your target is not normally distributed, it has a skewed distribution. In that case, you can apply some transformations to make the distribution of the target more like a normal shape, like a bell curve. For example, log transform usually prove to be very good in a few of Kaggle competitions. Like for example, in this, like there was a competition, Liberty Mutual Property Inspection Prediction. You try to predict the outcome of a property inspection, and on the x-axis you see a different XGBoost runs. These are random parameters. On the y-axis you see the score, normalized Gini in that case, and you can see how model actually varies. And on a green line, you see the green model, which is a logarithm by logarithm of 10. The variation of a model is less compared to the previous model. So standard deviation of these results will be way much smaller, which is actually good. That means your model is more stable, even though in some cases the other models outperform it. But actually in that case, we're just looking for a stability. Stability is usually better than just the best score for some single given point. So feature encoding, again, like, one of the interesting topic to discuss, that's like how you can encode your categorical features, right? Because most of the machine learning algorithms, they actually usually expect you to provide a numerical data, right? Like numbers, basically, right? Your category is like a gender, for example, or a color. That's something, but not the number. Obviously, the easiest way to do that, it's a one-hot encoding, which you're technically all familiar with. You also can do labeled encoding. That's a very simple technique. You just replace your category with some integer number. But it might be a very a bad interpretation, because in that case you introduce some order in your data. But in most cases, let's say in color, there is no order in the color, right? Basically, especially based on some randomly unsigned integers. So one hot is a good idea, of course, but it's sometimes, I mean, in some cases, if you have like a lot of levels in your category data, the data set becomes too huge. So as an example, right, you label and code, you have a three categories A, B, and C. You just map this category to some specific integer number and replace this number in your data set. For one hot encoding, as an example, right, you have again this three category, but you have to create three different columns to represent these three features. But there is one advantage actually of one hot encoding compared to a label encoding, right? That let's say if you have a new category, you can just, it will be all zeros, right? Basically, you have just your bias, and that's it if you fit a linear model into it. Also, you can do as a frequency encoding. You just can encode your category using frequency. So basically, you calculate how many times you see this category in your data set, and just normalize it, like divide by total amount of rows you have in your data set to get the frequency. So basically, you can think of it as a probability to meet this particular category in your data. So in that case, you can highlight why less frequent category is pretty good, right? Basically, C just you have a category C just 2 times in your data set. That means it has a very low frequency compared to the rest of categories. The disadvantage of that approach, of course, if you have, let's say, a category which has the same amount of frequency in your data, you won't be able to your machine learning model won't be able to distinguish them, right? Let's say if you have a 2B and 2C, they both have the same frequency. Yes, I also introduced the order, but in that case, order actually means something, right? Because it's a frequency, right? And basically, order in this thing actually it's a good thing, because that's usually I use this technique to fit tree-based ensembles, and tree-based ensembles usually looking for a best splitting point, right? So basically, I'm looking for the right order actually always. So my model will be able to split them, like easily. Okay, the next idea and approach, actually, you can use a target mean encoding. So you just, given the outcome you would like to predict and the features you would like to encode, you just replace each category with a mean of the outcome. In case of A, we have a 4A here, right? And we have it's 3 out of 4, it will be 0.75. Probability of A, given feature A, the outcome will be 1. In case of B, it will be 0.66. In case of C, because we always have like a ones, the probability of outcome being 1 given the category C will be always 0. Always 1. And seems to be like a very good approach, but you immediately see, let's say you have a less frequent categories, the information about them will be not very reliable, right? You just have 2 examples. That's, it's not very statistically significant, even though both of them actually ones, that doesn't tell you much, right? Because it's like, well, so what? It can be easily been by chance, right? To deal with that, we introduce, instead of like just encode by mean, we introduce actually a weighted average between mean of the level of our category and the overall mean of the data set. We also have a function which depends on how often you can see this level in your data set. The bigger the n, the bigger the lambda will be here, right? So, and that means your average will be more reliant on the mean of the level, not of the mean of the data set. So it's more like some sort of a smoothing approach. And usually that's a very good step function, which to sigmoid-like function actually to model this kind of idea. So basically, x here is a frequency, how often you have your category level in your data set. K is an inflection point. That's basically the point when lambda equal 0.5. In case of the red line, it will be like equal to 20. In case of the blue line, the k equal 2. And f actually, that's control of your steepness. Right? the less f you have, the more steeper your function. So blue line has less f, f over blue line is less than f over red line. If f equals 0, you have a stepwise step function basically, which has a which 0 until the inflection point and then goes to 1 after inflection point. So as an example, no. Sorry. Okay, so that's a function I'm trying to explain, and if we just run it for different case, you see we just shifting. Oh, I'm sorry. How do I? So basically, I'm running for different case from 0 to 4, and you can see how function actually, shifting from given the different inflection point. F controls the steepness of the function. So the bigger f you have, the more smooth your function will be. In case of equals 0, it will be like the simplest case when your f equals 0. That basically tells you, hey, if I have less than two examples of my category level, I'm going to use the mean of the data set. If I have more than two examples of my category level in the data, I'm going to use this mean of the level. That's it. By adding the steepness, you just smoothen the results. Like around 2, going to be 0.5. So let's go back to the, hey, no, oops. All right. So that's exactly the example what I just showed you. So in this example, the f is always pointing to 25. I'm just playing this k, right? I'm shifting it from 2 to 3. And you can see how predictions actually varies from this change, especially for C, right? For if k equal 2, that's exactly the amount of examples I have for C, the lambda will be 0.5, and I get the weighted average between the level of a category and the dataset mean, which is 0.75 in that case. If I move a k to 3, I immediately get the very small weight for mean of a C and a very big weight for the mean of a data set. So you can see, because I'm moving, the bigger k, the more conservative model become, and the more embedding closer to the mean of the data set. The less k, the less conservative it is. And it's closer to the, of course, it's closer to the level mean. So, yeah, what else can be done? Even in that case, even if you apply a Bayesian smoothing, a very complex algorithm like a XGBoost, for example, can find a leakage in this data set. So what you can do, you can join your categories, which has a small frequency in your data set. You can join them together to create merge them together to create a bigger category level. That's one approach. The second approach, you can somehow introduce a noise of your data into your data, and that's so instead of just blindly encode them using a mean encode, you can also use a leave one out approach. So basically, so you encode each category, each record, using the rest of the records. In this case, for the row 1, which has a feature A, you found all the rest of the A in your data and calculate the mean to get the mean of for this particular row. For the second, you do exactly the same, but you just exclude the second one. So it's a leave one out. You're always leaving one out of your data. And for a third and for fourth, you repeat this operation for all records in your data set, and it's kind of very time-consuming, I must say. But it's very reliable, especially if you have a small data set. That might be your weapon of choice. So as you can see, the data here is slightly different. So basically, you can think, again, as I mentioned, you can think of it as a way to introduce a noise in your data, which helps you to, which prevent the model from overfitting. Because in that case, model you're trying to fit on this data set should be more, careful, not blindly rely on one single column. You also, as one of a technique, you can, instead of leave one out, you actually can just add some noise to the found encoding. Of course, noise is supposed to be independent for each row. I'm pretty sure the noise should be not normally distributed. It should be more like uniformly distributed, because normal distribution, that's something that all machine learning algorithms designed for, right? Basically, it's very good in actually approximating anything which has a normal distribution. But expected value actually is, that's the way how you deal basically with a normal distribution always. So the second thing about adding random noise, actually, that's you have to somehow calculate the right range for your adding random noise. Let's say for binary classification, it's kind of easy to get what kind of range you would like to apply. But for regression task, it's not that easy to get the idea how exactly what kind of random noise you should add to your data in order to not overfit. Okay, the last technique, what can you use for categorical encoding, actually? That's quite well-known technique in a banking domain, which is called the weight of evidence. It's very easy. So basically, given the level, you just calculate the percent of non-events, your negative events, divide by percent of positive events, and just take a natural logarithm of that. To avoid division by zero, which can mean instead you just apply you just add a small number to the number of non-events in the group or events in the group. So to highlight what exactly I mean by that, I just write some simple example, right? So let's say we have a category. It has just one single non-event, right, which is 0. It has 3 events, which is 1s. So across the whole data set, we have 9 records, and we have how many? 7 positive examples. So I forgot to check that number. So basically, I'm sorry, it's supposed to be slightly different number. I just forgot to fix it. So it should be 3 divided by, oh no, actually that's right. Yeah. So for positive, it should be like 3 divided by 7, right? The total amount of positive events. For negative, it should be like 1 divided by 2. We just have 2 negative events in our data set. So it'll be like 50%. You repeat the same procedure for all category level you have, and now you can take a natural logarithm out of that, which gives you a weight of evidence. So that's another way how you actually can encode your category levels and your categorical data. What else can be done? This weight of evidence has a nice addition to it, which calls information value. You can calculate information value for weight of evidence, which calculates like as a difference between percent of non-events and events multiplied by weight of evidence, and you summarize it across your levels. This gives you some number. This number can be used to select, or actually basically it's your feature importance. So you can use this number to pre-select the features or categories you would like to use. A rule of thumb here is quite simple. So if information value is less than 0.02, that's not useful for prediction value at all. For up to 0.1, it's a weak predictive power. From 1 to 3, that's a medium. From 3 to 0.5, it's a strong. If it's more than that, it's a very suspicious column. You might have some leakage in your data. So you have to take a look what exactly you did. Maybe you made some mistake. Maybe like your data has a very long tail of unfrequent categories, which has always like say 0 or 1. So some investigation need to be done. But basically, if you try to fit this feature into your machine learning model, you will overfit. So what else can be? I mean, what else? What other nice property of this particular encoding? You also can use the same approach to encode your numerical values. But for numerical, you actually can, because you can calculate information value, you can play with a basic, let's say, you have a numerical feature. You can binarize it, right, by using quantiles, for example. But you also can actually play with these quantiles and merge some of them, giving an information value of the whole column. Or, for example, let's say you quantize your numerical value and you calculate weight of evidence. If your category level has the same weight of evidence, you actually can merge them together, because for machine learning algorithm there is no difference for them. They have exactly the same ratio basically inside. So why don't you bother actually keep them separate? Which is extremely useful for in case if you're trying to binarize and basically treat your numerical value as a categorical. So that's basically exactly. So the good thing about numerical features, you can use them as they are, right? Especially for tree-based models. You don't have to scale them, you don't have to normalize them, they're just good as they are. But you also actually can treat them as a categorical by binning them into quantiles or using histograms, basically, right? So basically you can use a bin of the same size, which is a histograms, or you can use a bin which has the same population inside, which is a quantiles. What can be done? As I mentioned, you can just encode them as using any categorical encoding schema, or you can just replace with a bin, means, or median. That's kind of approach. Usually it's very handy in case if you have a sensor data, especially if you have a sensors, you know, that's usually supposed to be across some values. But because sensor data usually oscillating all the time, so like, you know, we have a tiny little changes because of some error on measurement. But if you don't need the exact value, but you just need some actually, you know, like say a level approximation, that's the way how you can do it. Also, you can apply like a different dimensionality reduction technique to several numerical features to get the smaller representation of the same features. That's kind of could be useful for, again, for my intuition behind it. Say you have three numerical features. You can, using truncated SVD, you can just reduce them to one single feature. And that feature might be useful for tree-based models, because tree-based models usually vary better in approximating linear dependency. But SVD and PCI, because they're linear nature, then actually can quite good in approximation some sort of a linear dependency for you. So that will be a very good support for tree-based methods. Also, for numerical features, again, you can cluster them, right? You can just use a k-means to cluster them, and then you have a cluster IDs, which you can treat as a categorical again, and using a categorical encoding schema. Or, which is kind of very useful, you can calculate the distance for each row in your dataset. You can calculate the distance to the centroids, and that's give you like a whole set of new features. Not to mention about like, you know, a simple features like, you know, a power of 2, for example, square roots, or even, you know, like addition and multiplication, for example. So, yeah, we all know like basically random forest is a very good approximator. It can approximate literally anything. But let's say to approximate this kind of dependency for random forest, it took like a lot of trees actually to build. So if you just provide the, you know, basically the power of 2 features and the row features as well, it will require way much less tree to approximate way much better. So yeah, so that's kind of introduction to the next part, right? So basically, we're just trying to discuss like a simple approach how we can. Basically, we discussed like we had an overview of the tool, right? What exactly we can do with the features, how we can represent them in numerical form. But the thing is, how exactly we, let's say, find this, find the right representation, how we find different feature interaction to help our model to converge faster and maybe like produce a smoother decision curve. Well, of course, it requires domain knowledge. You can analyze the machine learning algorithm behavior. Like, you know, you can analyze GBM splits. Well, obviously, you can analyze linear regressor weights, for example. That's something I would discuss on the next meetup on advanced feature engineering, especially because, you know, let's say you have, so in case if you have the question is how can you encode different feature interactions? Well, for numerical features, you can add different mathematical operations. You also can use a clustering or, let's say, k-nearest neighbors to, to create some features for you. If you have a pair of categorical features, you can use them. You can combine them together, treat them as a new category level, right? And you have, let's say, you have a pairs of category, and you just can encode them using any provided schema as well. If you have a combination, you would like to encode the interaction between categorical and numerical feature, you can, for each categorical level, you can actually calculate different statistics of numerical features, like a mean, median, standard deviation. Usually mean and standard deviation is quite helpful. Min, max might be, but it depends on the problem you have in hands. So feature extraction, that's something. Yeah, given the raw data, you would like to extract some features. For example, if you have a GPS coordinates, you can download the third-party data set, which provides you, let's say, you can map basically GPS coordinates to the zip codes. Knowing the zip code, you can get information about population or any other different statistical information. If you have a time in your data, you can extract the exact year, month, day, hour, minute, like time ranges, or like if you have a holiday calendar, it's actually usually helpful for retail chains. You can you can have a flag, is it holiday or not, for example, or what kind of holiday you have. As I mentioned before a couple of times, you can actually tune your numbers, like say age into ranges, usually quite helpful, especially for range, for age. Well, for textual data, like a classical approach is a bags of words, obviously, but we all know that. So I won't stop here actually. Yeah, of course you can use a deep learning for that as well. Especially you do a word to vec or doc to vec embedding. So, and the beauty of it actually, basically right now you don't have to train anything from yourself. You can use a pre-trained word vectors and use them like as they are in your model. You also can, for example, let's say you have a short documents in your data set. You can calculate a word, you can transform your words into vectors, and then calculate an average vector, and that will be your doc-to-vec representation of your data. And yeah, I think that's it. And I can have a question, guys. Thank you.
Questions on the website.
What?
Question, they say ask question on the website.
Lots of questions piled up, which is great. Are you doing a Redux talk at H2O World as well?
Yeah, I do talk, but it will be a different talk actually about a different topic.
If you want to know more about, there's more high-end, good, informative talks next week, Monday and Tuesday at the Computer History Museum, not far from here. At H2O World, if you're not signed up, I think there's probably maybe half a dozen or maybe a dozen seats left. Fully sold out, 700 people are signed up, but I'm sure there's a meetup giveaway. I don't know what you guys are doing, but
it's going to be a surprise a little later.
There's not just Dmitry is speaking again, but there's a lot more really exciting speakers. It's really interesting.
Yeah, we're going to have a Kaggle #1 actually on our panel, and Mario's Kaggle #3, former Kaggle #1 Grandmaster, is going to have a talk and be on a panel as well. And I'm going to be in a panel, and I'm going to have a talk, and yeah. It's going to be.
Before you run away to all the questions, could you go back for once more on that? You should make a GIF out of that the feature engineering where you do how the target encoding is happening.
Leave one out, you mean?
Yes, leave one out.
Yeah. Yeah, we can have a GIF file actually. That's a nice idea. All right, so.
Awesome. Thank you all for submitting questions. If you still want to submit some questions, just use the Slido hashtag. We'll be answering them now. All right. So Dmitry, what I was thinking we could do, and hi everyone, I'm Rosalie. I'm our Director of Community. So thank you all for coming tonight. Dmitry, I figured I could just ask you the questions if you'd like. Yeah. Perfect. Okay. So first question for you. What are the cases where it took forever to compute, and what did you do about it? Are there specific hardware or configurations so it does not take so long?
To compute what?
let's see.
Oh, to compute, okay.
Yep.
So, well, depends exactly what we're trying to compute. If we're just trying to compute something like, let's say a target encoding, well, in that case, usually that's because I wrote a shitty code and I just have to rewrite it. If it's let's say a machine learning model I would like to, to speed up, I might switch to a smaller model. I might subsample the data, or because I work on H2O, I have access to like a cluster. Basically, I can spin up H2O cluster and run it on a cluster. That's actually exactly what I do all the time. I just borrow the cluster from H2O.
Perfect. Okay. So it says here, is frequency encoding similar, same as Huffman encoding, which is used in communication systems?
Yeah, I think so, actually.
Okay.
Yeah, very close.
Okay.
I think it's exactly how I found it for the first time.
Perfect. How can one decide which is the best category in coding?
By random chance. I mean, by checking all of them and find the best, basically, right? It requires some gut feeling. But let's say from my expertise, target encoding usually prove to be the best. Like, let's say it's a weapon of choice.
That was my question, but I want to which metrics do you use?
Oh, which metric? Okay, that's a good. Well, obviously it depends. The metric actually depends on your business problem you're trying to solve, not about it's nothing to do with. So the whole setup actually, you have a raw data, you're trying to do different feature engineering, you fit it to your model, you check it on your validation set using the metric you select actually with a business, and that's how you get results. If you get a significant improvement, you apply this feature as well. If you don't, well, you try it again and again and again. So it's really mostly like the metric actually it's a business question, Let's say I have a very good example, then the company actually would like to predict something, and at the beginning of the quarter, there was actually okay, if you overpredict or you underpredict. But as soon as you're getting close to the end of the quarter, the overprediction actually cost them so much money. So they would like actually to be like smaller. But that requires you to design a metric yourself, basically. But again, it's nothing to do with the feature engineering. You can use exactly the same features. You just see how your model actually fit to the metric of choice, basically. So, but mostly what you can do actually, let's say if you have a AUC as a metric and you have a binary classification and AUC as a metric, in that case, you can encode your categories and immediately actually check it against AUC because, obviously that's very easy to do. That's something that can be done. Same goes for, classical metrics. If you have RMSE, for example, and you would like to encode a category, so basically your category encoding, especially target encoding, it's a small, simple model by itself, right? Because and you can directly measure it if you like, but it's not something I actually highly recommend because still, in most of the practical cases, that even though this simple comparison can be good, the final model can be bad actually. So there's no guarantee.
Another question from that attendee, they're curious what to do with a feature with a very large categorical values.
You mean then you have a lot of levels? Oh, that's basically that you can apply both techniques at the same time. You can do a smoothing and leave one out. Leave one out is extremely expensive, but instead of leave one out, you can do actually cross-validation. You just split your data into 5 chunks, for example. You try to encode them using 4 chunks and apply this found encoding actually to a 5th one. And you repeat this process for all 5 categories. Obviously, the fastest way is just to apply random noise, which could be a replacement, but in that case, you have to design it carefully. I didn't include random noise here just for one reason. I don't have actually, an understanding actually what kind of noise to add, what's the rules actually of adding noise. So that's why I don't have it in my slides.
Awesome. So many great questions coming in. Thank you all. Another question. It's claimed that neural networks will make feature engineering obsolete. What do you think and why?
In image recognition, in speech recognition, in what else? In textual data, maybe? Yeah, definitely. That's exactly why how we do. So basically, as soon as you have unstructured data, like image, sound, definitely that's the best way. They can design features for you. If you have a structured data set, like the data set we work on, you have a database, you have a lot of data which is structured. Not so great, actually. Usually they perform poorly compared to like a tree-based methods, especially if you do methods empowered by a smart feature engineering. You still can actually use them, the neural nets on a feature, on a structural data, but it still requires you to carefully prepare the features for it. So it is an active area of research, I'm pretty sure, but it's nothing like, nothing smart actually. Still, we're just waiting until for final results.
Awesome. Any techniques on feature extraction for time series or historical data?
Yes. A lot of them actually, but most of the things you can do with different lag features, right? That's obviously what you can do with your time series data. The key to success here is it's a carefully apply your validation schema, especially if let's say if you would like to predict something like 2 weeks ahead, for example. In that case, given the data, you can't use your last 2 weeks of your data set. Your features should be created on the previous data, yeah, the key here, by your validation set, you're trying to model the actual real-life scenario. So that's basically, that's the most. But lag features, usually exponential smoothing, very helpful. When you're just trying to, that means your most recent events actually more important than the previous events. But basically, that's it. If you given the tree-based methods, of course. Of course, you can apply different technique like ARIMA but it's not that fun.
Awesome. So I'm seeing, will you post a presentation online? Yes, we will. You can find it on our YouTube in a couple days. What are the methods of encoding a list of elements?
That depends. If list has a sequence, if they order it somehow, you can just create them as a separate columns. If there is no sequence in it, well, obviously you can one-hot encode them, right? Because that's something that usually you do in marketing. That's how you actually deal with kind of events. Usually it's a very common task in marketing when you given the set of events, you're trying to predict user behavior. Or let's say given the user click events, you're trying to predict something out of a user. And no, let's say I do have a couple of ideas, but they need to be checked before I can share them. But obviously, it's not very easy compared to the given problem.
Awesome. Can we pile up all these methods together and run the model and find out the best one?
That's something you can do. Let's say using it's more like you can do that. Although usually it's very expensive. Say you have a data set which has 500 columns you would like to know, you found useful. And you have if some of them are categorical, you have to encode them using every given categorical schema I showed to you. And then you have to apply, let's say, feature selection methods, which could be, let's say, feature elimination, usually. Or you can fit a linear model and, use an L1 regularization to get the feature which has weights. But it's no, I don't think it's a good idea. Usually, if you just do it iteratively, you get the better results. Because the feature selection methods that are available right now, they're not very reliable, let's say, in terms hey, I found 10 features out of 100. That doesn't mean actually it found all of them. You might still have some random features inside. You can still have some feature actually missing. So I wouldn't recommend that actually. So usually it's, one by one, feature by feature, I think that's usually provide you more stable solutions.
Great. Can you do target mean encoding with H2O flow?
No.
Okay.
We can do it with our product, which I forced to work on. But, yeah, I was actually instructed. We don't not to mention it. So.
Another great question. Thank you all for the questions. I see more just coming in. Have you come across examples where feature engineering was applied in physical security, especially in a domain like banking?
In banking, yes.
Okay.
And yeah, let's say a fraud detection and anomaly detection usually apply and use a different tool set to do the same stuff. It's more like, yeah. We should actually invite Ashit. He can do he can talk for days about that. I'm pretty sure.
I will make a note on my Trello. Question here. Let's see. Is there any good feature encoding tool, for example, a tool to help compute target mean encoding?
Yeah, I think there is some actually scripts in the wild for Python. I don't remember the links, but obviously you can find the ready script for Python for sure on Kaggle site. Just Google it, go on Kaggle and Google target encoding. You also can try, just a lucky search on GitHub. Do exactly the same. Just Google GitHub for target encoding. I'm pretty sure you find something. I might, let's say, if I found the package I'm referring to, I will post the link on a meetup on a meetup page.
Awesome. How to deal with complex objects having partially unknown attributes?
Can I have an example? What exactly meant by that?
For example, that you're including users, right? And we don't know his age. Okay, so user is a person of an age, and then.
Oh, you're talking about imputing, right? Basically, say we don't have some information about user is missing.
Yeah. So for some users we got that information. For the others we don't have that.
Yeah, let's say we don't have an age for one particular user, we have for other. Well, it depends, right? So you can apply different imputing techniques to do that. Like obviously the simplest one, you can just replace missing values by a mean. Just kind of stupid, but it works in some cases. It also depends. Sometimes your missing values can be due to the mistake, right? They're not supposed to be actually empty, but they're empty. It's a mistake in your data gathering process. Sometimes missing value actually can mean something. It can be an information. Hey, value is missing. So there could be some reason behind that. In that case, you can actually leave missing values as they are, and basically modern methods like XGBoost can actually handle missing values pretty easily. You can just pass it, and I think it's usually on each split it decide where exactly to pass all the missing values, depending on the loss function. So and it goes to the tree, and basically on each split it decide left or right. He put all the missing values. So it's a pretty powerful technique. In case of encoding I described, let's say for categorical, you just treat the missing values as a separate category, and same goes for numerical values. It's a separate bin. But I would try, one of the rule of thumb, you replace your missing values for numerical, you replace it with a mean, and you also add a flag feature, binary feature, which tells you hey, that was a missing value actually, 0 and 1. So basically instead of one column, you will have a 2. But usually that's a good starting point, especially for neural nets and linear models, because you're keeping the both information. You replace it with a mean, which actually, in that case, you won't ruin your normalization schema, but you also keep the information that was actually a missing value there. So it's usually very helpful.
Awesome. Do you prefer certain models for categorical data, such as random forests?
XGBoost mostly, but yeah. Again, it depends, right? Because let's say in case of the events, like you have a list of events. Obviously, that's like what I could do immediately. I'll just replace everything as one hot encoding and basically fit a linear model to see what happens. And usually, because events is a very sparse and like a very, very wide space, that's enough. It's already provided you a very good model.
Okay. Any other questions? I think we're good on questions here. I was actually just going to pass the microphone around if anybody wanted to ask any questions. I mean, if you do, just raise your hand and I'll come on over. All right. You're like, I'm going to read it from there.
Yeah. So, you were talking about combining categories into one if they have almost the same predictive power. So it makes sense if your model is completely statistical. But what if? So does it mean that you can combine them by the same prediction power only after you made sure that your features are independent? For example, you did some primary component analysis.
Let's say for given model, right? Because Europe. All right. So basically, that's what the model actually sees, right? See in the data, right? So basically, because I always see the same weight of evidence number, actually the model itself has already combined them, right? I mean, there is no way to distinguish, let's say, is it with this 0.4 value for A category, this 0.4 value for B category. So it's already done, basically, right? But it can be a good idea, you know, let's say it can bring you a good insight for numerical features mostly, right? Because that shows you can actually combine the bins. But although, yeah, let's say, it does make sense to combine like a neighbor bins, but if you have, like, say, a bin 1 and bin 10 with the same weight of evidence, it's kind of strange, right, to combine them, obviously, yeah.
They have like natural order then.
Ideally, yes, but it's, you know, even, let's say, yeah, this March on GTC conference, there's a paper about how you can actually, you know, predict the anomaly using recurrent neural nets, and that's exactly what they did. They binarized their numerical features, but they force neural nets to always keep the same order of them. So they try to learn embedding, but if embedding, let's say, like this, for example, it should be in ascending order, right? If embedding actually in right order, they just shift the weights. So all the time, right? So it's kind of a strange idea, but they always, like, you know, force numerical values to have the same natural order that they're supposed to have.
And we're live. All right, who is next? Over here? Okay. Oh, okay. I'll have you go first, and then I'll have you go first. Okay.
Yeah.
Perfect.
So when we are using frequency for some feature, and then we want to apply the model and predict, and then comes the real input, how do we get the frequency then?
During your training, you learn the mapping table, right? If you have a test data, you just apply this mapping, you use this lookup table to the training data, to the test data, I'm sorry. So basically, this data is never changed during the inference process. You learn this frequency out of your training data. If you have a new data set, like a test data set, you try to predict, you never calculate anything. You just use the found values. Which immediately brought the question, actually, what if I have a new level, right, in this data set? Well, you can apply missing values if your machine learning model actually able to handle missing values. So you can just say 0, because you never saw this data during your training. It's
Okay.
Perfect. Thank you much. All right, so I'm coming up here for you.
How would you compare the H2O's use of categorical variables, which you can learn directly from, compared to using feature encoding?
not sure I'm following your question.
Well, H2O supports categories as inputs to...
Yeah, but it's under the hood, it just encode them using one hot encoding. Or it can encode them, or it can do one hot encoding and then just do a dimensionality reduction. It's just done, you know, you never see it by yourself. And the third way, it can do a label encoding. That's all that H2O does inside. You just don't know that, but that's it.
Okay, I just never quite figured out what they did do. I
They
know
just-
with
it's
with
very
deep
simple.
learning they do
Deep
automatically-
learning,
they do,
no, we don't do
coding.
embedding anyway. So that's what you're referring to. It's, hey, we have a lookup table. Why don't we just learn the weights? Yeah, there is a common technique in neural net, but H2O deep learning does not do that. It still do one-hot encoding, but it can do it on the fly.
But I think for trees it does use the categorical variable directly.
Yeah. No, not directly. So it's you have to have some numerical representation because that's how you're able to build a histogram on it and use this histogram to find the splitting point of it. So there is one approach which trying to use a categorical values directly. There's a company called Yandex, and they recently released a cat boost decision trees, and they stated this cat boost actually able to handle categories, as they are, like raw categories data. But I didn't check it myself. The results are kind of controversial. In some cases, it performs extremely good. In some cases, it performs like extremely bad. So, nothing in between.
All right, we got a question over here.
Yeah, I have a question. You mentioned gradient boosted decision trees or regression trees. And so I have a question, which is probably, it's not directly related to this lecture, but I think it could be of interest to many people. So for example, when I used to work on query URL ranking, then gradient boosted regression trees, they worked quite well. And recently, actually about a couple of weeks ago, I tried to use this kind of boosting with deep learning in computer vision. So basically what I did, after we trained the network, I did the inference on the whole train set, and those pictures that did the worst results, they were like prioritized, so they were randomly selected more frequently. And this didn't work at all. So what is, in your opinion?
There was one paper actually about how you can boost CNN. You can Google it on arXiv. I think it's called Boosted CNN or something. They tried to learn, there was a specific architecture they tried to learn, first of all. But they got a pretty good results, but I tried to repeat them, but, well, kind of. No, it was pretty good, but yeah, I wouldn't say it's the best of the class. There is another technique you actually might find helpful. I think it's called online hard example mining. That's something you can actually try for yourself. Idea is quite simple. Given the batch, right, you calculate the loss. You have a gradients, right? But you backprop only the gradients of the examples, which was the hardest one. Not all of them, but just the hardest one. But of course, there is a question how actually to define the proportion and all this stuff, but I haven't read the paper, I don't have the details, I just know the idea.
But the difference between what you're saying and what I was mentioning, that I try to determine the worst ones by just full inference. But what you're suggesting, that we are still running it in backpropagation mode, which means they have like a drop and things like that.
I know.
So the loss is not real loss in that case.
To me, you know what, I think, if you ask my opinion, which is actually doesn't supported by anything, just my gut feeling. You see, in boosted trees, each and every tree are different, right? Basically, it's shaped differently depending on what exactly it's trying to predict. In neural nets, you always keep in the same architecture. On each step, it's the same architecture, just weights. I think that's the biggest difference. Yes, it's a different model because you learn different weights, but it's not something that define actually a different model for in that case. It just that's my gut feeling. I don't know actually. It's just because I did exactly the same as you did. I just try, hey, what if I just fit a neural net inside the boosting schema, which is kind of easy to do in scikit-learn actually, right? You just apply method and you're done. Nah, didn't work at all. I mean, the first one is good, and that's it basically.
Okay, thanks.
Thank you. Any other questions? If you raise your hand, I'll bring you the mic. Anyone? Okay. Let me check Slido real quick to see if folks maybe use that as well. Let's see here. Okay, I think that's all the questions, Dmitry.
Awesome.
Thank you so much for your talk tonight, and thank you all for coming.
Thank you.